welcome to our new segment. Today we're going to be discussing Lab 6. I'm your host, Jaren, and I'm joined today by our scientist, Hannah. Today we're diving into the fascinating world of capacitors and RC circuits, key components behind many of the electrical devices we use today. In this lab, we investigated how capacitors charge and discharge over time, and how this behavior is described using something called the time constant. Scientific literature tells us that an RC circuit, the time constant, defined as resistance multiplied by capacitance, represents how quickly a capacitor charges to about 63% of its maximum voltage. This concept is essential in electrical engineering and physics, with real-life applications in smartphones, medical devices like defibrillators, signal filtering systems, and timing circuits. Understanding this process allows engineers to design faster, more efficient, and more reliable electronics. Let's head to the lab footage where we can review what we did in the lab.
Hi, I'm Hannah, your local scientist. Today we're going to be going over the materials in this segment. So to carry out this experiment, we use several key components. A capstone signal generator, which produces a controlled electrical signal. In this case, a square wave used to repeatedly charge and discharge the capacitor. Next, a voltage current sensor, which this measures how voltage changes over time across the capacitor. The resistor, which we had 10 ohms, which limits the current and controls how fast the capacitor changes. So the next one, capacitors. We were at 330 microfarads and 100 microfarads, which store electrical energy. Then we used a current table. A circuit table. I'm so sorry. Circuit table used to physically assemble the RC circuit and connecting wires which complete the circuit and allows the current to flow. Each component plays a critical role. The resistor and capacitor together determine the time constant, while the sensor and generator allows us to observe and measure the changing behaviors in real time. Thank you.
In our lab footage, you can see us do a couple of things. First, you can see us set up the RC circuit by connecting the resistor and capacitor in series with the signal generator. We've set the signal generator to produce 1 Hertz square wave with a 5 volt amplitude. This means the capacitor will charge and discharge once every second. The recording was set to 3 seconds and the sampling rate was increased to 500 Hertz to capture a detailed data from this fast process. You could also see us placing voltage sensors across the capacitor to measure how the voltage changes during charging. Once the data was collected, I noticed that the team zoomed in on a single charging cycle. They identified 2 important points: the time when the voltage was 0 volts, and then the time when the voltage reached 63% of its maximum value. The difference between these times gave the time constant. And we repeated the experiment, but this time we added another capacitor in parallel. This should increase the total capacitance and change the time constant.
I'm assuming it's solids, right?
Right?
I think so. Should be. So, zoom out.
Now we're going to be going over the graphs and the tables for the data and data analysis segment. So Taking a closer look at the data collected during the experiment, for the first setup with the single capacitor, the time was at 0 volts and at 0.498 seconds. Time at 63% voltage was 0.505 seconds, and the time constant was 0.007 seconds. Using this time constant, the experimental capacitance was calculated to be 330 microfarads compared to the theoretical value of 310 microfarads. This resulted in a percent error of 6.4%. This small percent error indicates that the experimental results were very close to the theoretical values. The graph shows a rapid increase in voltage at the beginning, which gradually slows down as the capacitor approaches its maximum charge. This matches the expected exponential behavior described in theory. For table 2, the time was at 0 volts, or time at 0 volts, and it was 0.498 seconds. And then time at 63% voltage is 0.510 seconds. And then the time constant was 0.012 seconds. And again, this is with the second setup with capacitors in parallel. The experimental capacitance was 430 microfarads, while the theoretical value was 400 microfarads, giving a percent error of 7.5%. As expected, the capacitance increased when the capacitors were connected in parallel. This caused the time constant to increase as well, meaning the capacitor took longer to charge. Overall, the data supports the relationship of time constant equaling RC, showing that increasing capacitance increases the time constant. We're going to be reviewing the experiment as a whole and just reflecting on what we did in the lab. So, Hannah, what did we learn from this experiment?
We learned that the charging and discharging of a capacitor follows a predictable pattern, and this describes by the time constant, by measuring how long it takes to reach the 63% of the maximum voltage. We can determine the capacitance of the circuit. Our experimental values were very close to theoretical ones, with percentage errors of 6.4% and 7.5%, showing very good accuracy, because that is below 10%.
Let's address some important reflection questions. So first, what caused the percent error?
The percent error was mainly caused by measurement uncertainty when reading the graph, as well as small inaccuracies in the sensors and the circuit components.
I see. How could this setup be improved?
In a few ways, we could improve accuracy by using more precise instruments, minimizing extra resistance in the circuit, and repeating the experiment multiple times to average the results.
I see. Were all the time constants similar?
No, they were not exactly the same, although they were somewhat close.
Should the time constant be different?
The time constant should be different. Since the time constant depends on capacitance, increasing capacitance, like we did with the parallel capacitors, it should increase the time constant.
Oh. What about the percent errors? Were they similar?
They were similar, but they weren't identical.
Well, should the percent error be different?
Yes, small differences are expected because each setup has slightly different sources of uncertainty, such as connection quality on measurement precision.
Where is most of the error coming from?
Most of the error likely comes from human estimation when selecting points on the graph, limitation in sensor precision, and small amounts of extra resistance in the wires or connection.
Why do these errors matter?
Understanding error helps us evaluate how reliable our results are and show us how to improve future experiments. Even small errors can be important in high precision electronics.
Thank you so much for your time.
Thank you for
It's
having
very
me.
illuminating. And in terms of credits, I'm your host, Jaren, and my co-host / scientist,
Hannah Macias.
And just kind of going over everyone's involvement in the lab. I'm Jaren, which was the host / journalist.
I'm Hannah. I was the scientist.
We also had Damien, Adam, and Remington. And we all worked and collected data together and helped create the PowerPoint as well. Thank you.